Hello and welcome back everyone to ptet.chemistry channel. In this video, I'll talk about hybridization in relation to hybridization of orbitals used for forming covalent bond. So this video, I guess to understand the contents within, you would most likely would need to align it with your understanding of VSEPR. And in actuality, hybridization of orbitals is what we use in order to justify the valence shell electron pair repulsion theory. So these two concepts are related to each other. Yeah? They shouldn't be treated as independent, but I've chosen to break them up into a different video simply because these are things we will have covered in different lessons, and it would have been too much to cover everything in one go. Alright, but once you understand the concept, you'll be able to apply across different settings. So that's what I hope to achieve with this particular video. Alright, so we know about hybrid being a mix, okay, a mix or a mixture, okay, and then we are talking about orbitals in relation to atomic orbitals. Alright, so we talk about orbitals and we talk about shells, subshell, and orbital in the other video on electronic configuration. So there was quite a long video because I thought it was much better to cover everything in that particular video because they're all related to electronic configuration. I also mentioned in that video that it's very important to understand atomic structure, which relate to electronic configuration, which relate to, well, hybridization, which involve a little bit of structure and bonding, but mostly bonding idea, which in turn relates to the shape of molecule under VSEPR. So these concepts are interdependent, and one story leads to another. So if you have fundamental flaws in any of these concepts, then it's going to affect your understanding and application in even more advanced chemistry. So I would advise you to always brush up your basic and get reacquainted from time to time, and once you know the basic story, you're able to tell it to yourself and anyone else, then you should be able to apply it in a different setting in further chemistry when you go higher up. Yeah. So mixing of atomic orbitals. All right, so we know in terms of electronic configurations, so let's just talk about carbon. So it's got 1s, 2s, and 2p. So it's got the shell number 1, and these are shell number 2. But then you also have these subshells, okay? So these are subshells, the collection of them, they are subshells. Each of these is orbital. So the s orbital and the p orbitals have different shape, being spherical, being dumbbell in shape, and these are degenerate, they have the same energy. That's why I draw them as same level in energy. And they oriented themselves in different directions, the px, py, and pz, because electrons occupy space as well. They whiz around the nucleus of an atom, right, in that fixed region of space, what we call orbitals. All right, well, in what we call shells, sorry, but these particular subshells are further divided into the different orbitals, which orient themselves in different directions. So for carbon, which is a 6 electron atom, we are going to fill in with parallel spin, and then we pair them up because there's no other place for you to have parallel spin in the s orbital. Then 2s, you fill with lowest energy first, and then that is the configuration, electronic configuration for carbon atom. Okay, when you form bond, we are using the valence shell electron. So these are n equal to 2. That is the outermost, or what I normally call as the valence shell or valence electrons. Yeah. Well, n equal to 2 is the valence shell. The electrons within are the valence electron or the outermost shell electrons. Yeah. We talk about forming covalent bond because we're going to share the electrons. Okay. Can you see that the 2s and the 2p are of different energy? The 2s and 2p of carbon, different energy. When you are of different energy, you don't form the bond straight away because then your bond will have different energy. But imagine if we want to form things like CH4. Okay, if you want to have CH4, I'm going to draw the three-dimensional structure to show the tetrahedral geometry. based on what we know from VSEPR, 4 sigma bond, 4 bond pair, no lone pair because the carbon uses all the outer shell electrons for bonding already. So the 4 bond pair repel equally, giving you tetrahedral geometry. Okay, so here the carbon has formed 4 covalent bonds. It has used 1, 2, 3, 4 of its outer shell electrons for bonding. This is the outer shell electrons. They have 2s and 2p. They are of different energy. These are all CH. Are they saying that the CH are different energy? Not really. The CH bond in each of these are of same energy. You can have a look at data booklet. All the CH bonds are already of the same energy because it has undergone, this atomic orbital of carbon have undergone hybridization, where you mix them together so that it will give you 4 sets of let me get this right. Let me explain it and then hopefully it will make more sense. Yeah. If I have the carbon atom, so I'm just going to talk about the two, maybe I just put a 1s in there. So the 1s is inner shell electrons. They are not used for bonding. Yeah. So in chemistry, we always talk about the outer shell electrons being the reactive one. Okay. So what you're going to do is you want to form 4 covalent bond. You want to form 1, 2, 3, 4. You want to form 4 sigma bond. Okay, so that is 4 bond pair. Specifically, not just 4 covalent bond, but 4 sigma bond. And we only count the sigma bond for bond pair of electrons when we did VSEPR, right? We are going to use this thing here, okay, for your hybridization. So this is before hybridization. This is just carbon atom, all right? So what does it mean by hybridization? Hybridization means you are going to mix, okay? Mix the orbital. You're going to mix the orbitals. Why? Why would you do that? Because they're of different energy and you want them to average out to the same energy before you actually use it to form the bond. Before you use the atomic orbital, the electrons have to be of the same energy before they form the covalent bond. What can you do? Well, this is what you can do. Okay, so that energy level is going to go somewhere in between. When I average it, I will get 4. How did I get 4 orbitals? These are what we call hybridized orbital. Previously, they are what we call atomic orbital. Atomic orbital because it's just of an atom. You haven't mixed in anything. The 1s remain 1s because you're not using the inner shell electrons for anything. Now they are all of the same energy. They are now what we call the degenerate hybridized orbital. So you fill in with 4 electrons. Because they are now degenerate, you do not pair them up anymore. You pair them up here because 2s is of lower energy than 2p in the atomic configuration, in the electronic configuration of the atom. You have mixed them together. When you mix them together, you average out in these hybridized orbitals. They become of the same energy. You want to form 4 sigma bond. That's why I have to mix in 1, 2, 3, 4. 1 orbital plus 1, 2, 3. 1 plus 3 will give me 4. These are atomic orbital. This is hybrid orbital. Why do I want to form 4? Because 4 sigma bond. Okay. Therefore, give you 4 bonding pair. That's very important. What have I done? Okay, what have I done? This is now another important concept. I have taken S and I've taken P. So I've taken 1 times 2S. I have taken 3 times 2P. So what do I call this then? These are what we call hybridized orbital, right? But there's a special name to it. There is 1 of the S. There is 3 of the P. This is called sp3 hybrid orbitals, or people just call it sp3 orbitals. How many of them do I have? I have 4. Okay, I mix in 1 of the 2s of carbon, 3 of the 2p of carbon, and I get 4 sp3 hybrid orbitals. They are what we call degenerate. They have the same energy now, unlike this. That's why I have 4 parallel spin like that. And then there's my 4 electrons that's being shared by the 4 hydrogen, each of them forming 1 sigma bond. Okay, so what does it mean in terms of in terms of what was I gonna say? In terms of the shape, the shape. Okay, individually you will have the spherical, you will have the x, y, and z. The axes are arbitrary here. This is your spherical s orbital, and then you will have the dumbbell shape of the p orbitals in this axis, whichever. So these are the p orbitals, px, py, and pz. These are dumbbell. When you have 1 times 2s and 3 times 2p, when you mix them together, 1 orbital plus 3 orbitals, they mix together to give you 4 hybrid orbitals. Because you mix 1 of the s, you mix 3 of the p, you get sp3. Okay, in an sp3, you can imagine, well, I hope you can imagine, is roughly 25% s contribution. It's gonna look 25% like s because out of the 4 things in there, only 1 out of 4, which is 25%, 1 out of 4 is only 25%, is s orbital. So you're going to get something which is how do I say this? Not a lot of s, but quite a lot of p. Quite a lot of p. So p will look like that. That is a perfect p. But now I have a little bit of s, but not a lot of s. Okay, so not a lot of s. Okay, more of p. Okay, and you will get 4 of that. So I'm not the best artist in the world, so I can't draw it properly. You have seen it in books. Okay, but the idea is important. Mixing our orbitals to get the hybrid orbitals of the same energy, so that when they combine to form the covalent bonds, they will give the covalent bond of equal energy. This become known as hybrid orbitals when you mix in 1 of the s, 3 of the p, 1 plus 3 will give you 4. Therefore, they give you 4 sigma bond because there are 4 sp3 hybrid orbitals. Okay, this is tetrahedral geometry. In every single carbon that has 4 covalent bond, in every single carbon that has 4 sigma bond around it, that means 4 bond pair, 0 lone pair, it will be a carbon sp3 hybridized. Okay, because 1 plus 3 give you 4 sigma bond. Okay, and that will tell you that it's 109 degree tetrahedral. So very common in alkene chemistry. Yeah. Okay. How about when we have alkene then? When you have things like alkene, let me just draw a very simple alkene. In fact, not just alkene. I can show you that. Okay, actually, yeah, let's do that because in AS this is what you do. You also do ketones and aldehyde, which you might not have heard of, but does not matter. The carbon is bonded to 2 other things, and it has a double bond oxygen. And then you might have also done benzene, which is carbon like that. Okay, and then you have H, 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 and H. So this is alkene, this is ketone, or you might know as aldehyde if this is H, but does not matter, it's just carbon double bond oxygen. The carbon form 4 covalent bond, the carbon form 4 covalent bond. This is what you call a benzene. You would do it in A-level chemistry regardless of whatever examination body you do. Okay, each of these carbon form 1, 2, 3, 4. Each of these carbon in this molecule form 4 covalent bond. Okay, but we are interested in the number of bond pair. Okay, the number of bond pair is equal to 3. The number of lone pair equal to 0 because we are looking at sigma. Imagine you are at 1. Imagine you are just at 1 carbon because shape of molecule or geometry is always about 1 particular atom. Yeah. So here you have 1 sigma plus 1 pi. Here you also have 1 sigma plus 1 pi. If you know the structure of benzene, you will know that this is not entirely true for the structure of benzene, but I'm just simplifying it so that you can see and count exactly. This being a double bond is 1 sigma, 1 pi, so there's 1 sigma, 2 sigma, 3 sigma around this carbon, 3 bond pair. But no lone pair because it used all the electrons, 1, 2, 3, 4. It used all 4 for forming covalent bond. Same as here, 1 sigma, 2 sigma, 3 sigma. but it uses all the electron for bonding because it has formed 1, 2, 3, 4 covalent bond. Same deal with the alkene here, yeah? So in terms of the energy and the hybridization that we need to consider, so the 1s, the 2s, 2p. So we know there is 1s2, 2s2, 2p2. So there's the carbon atom. That is unhybridized. We want 3 bond pair because we want to form 3 sigma bond, right? That will give you trigonal planar geometry about each of these carbon, whether you're in alkene, carbonyl like this, or in a benzene ring. Using a trigonal planar geometry and 120 degree. So there's 120, 120, 120, 120, 120, 120, 120, 120, and 120 degree. Okay, so that was unhybridized. So what do we want? Well, we want this. This is what we want. We want 3. We want 3 only. We want 3 sigma. Therefore, we want 3 hybrid orbitals. We want 3 hybrid orbital. Okay, we always involve the s for bonding because they got to mix. Because you got 2 electrons here, you got to mix into 3 of them such that there are no more paired electron in the s. All right. Okay, so you will also have 1 of the p. This is, you see, I've drawn them same level as the p, whereas this one is gone slightly down. This has gone slightly up. That's why it's hybrid. It's an average. Yeah. So what is this then? This is 1 time 2p unhybridized. Unhybridized means not hybridized. Not hybridized means not mixed. Not mixed means the energy doesn't change. Why do I have 1 there? Because I only need 3 hybrid orbitals. Why I only need 3? Because I only form 1, 2, 3. I only form 3 sigma. 3 bond pair, 3 sigma bond. I only form 3 sigma bond. Pi bond is formed in a different interaction, yeah? And we'll talk about pi bond, which has to do with that later on, okay? The 1s remains as that because you don't react the inner shell electrons. You react the outermost shell electron, which is the 2p and the 2s. You will get 4 electrons. The thing is, you do not fill in the 4 electrons in here. Where does the 4th one go? The 4th one remains on the p orbital. Why? Because you do not hybridize it. If you don't hybridize it, you don't mix it in. If you don't mix it in, why would the electrons be there? This obviously is quite wrong because of Hahn rule saying that you should fill in with opposite spin with the lowest energy first, right? But remember, this is an active species, and I'll tell you straight away, hybridization is a man-made concept to understand bonding better. Okay, we cannot, this does not exist in reality. Okay, so this is just a concept to help you understand bonding. Because I only have 3 hybrid orbitals, what does that mean? I have 1 of the 2s orbital. I used only 2 out of the 3 2p orbital. I have 3 orbital originally, 1, 2, 3. I only used 2 of them. Then I have 1 more unhybridized. Okay. So I have 1 of the s, I use 2 of the p, I get sp2 hybrid orbitals. When my carbon form 3 sigma bond only, 1, 2, 3, 3 sigma bond only, it will have sp2 hybrid orbitals because 1 plus 2 is 3. Okay, these are carbon sp2, these are carbon sp2, these are carbon sp2. I'm looking specifically at the circle carbon, yeah? So working out the hybridization is quite easy. Do not work from scratch. This is just for your understanding, okay? So what do we know? This is the carbon sp2 hybrid orbital. Now the next question really is, unlike the alkanes, unlike these compounds here, where there is no double bond at all, here you have double bond, and double bond. What does it mean? Well, it comes down to, what is this? Unhybridized. What is this? Electrons. So what will you do? So let's take the first example of the alkene there. Okay, so you have mixed an S and a P, 2 times P, which could be either one, whichever one, either 2. Okay, so in sp2, there's roughly about 1/3, which is 33% S character. The more S character you have, the lesser P character you will have. So it's getting smaller. Maybe not as small, but it's definitely smaller than the, sorry, it's definitely bigger than the, I mean, one of them is getting smaller than the sp3. Again, I said I'm not very good at drawing, yeah, but it's no longer a pure dumbbell shape, it's a mixture of these two. All right, I better get on with the orbital diagram, which I'm better at doing. So this is normal sigma, 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 sigma. So what does it mean? This is also a carbon sp2 because this carbon form 1, 2, 3 sigma bond. So 1 plus 2, 3 hybrid orbital because 3 sigma bond. Okay. I have an unhybridized p orbital. This is the unhybridized. Unhybridized meaning not hybridized. Okay. This is the unhybridized 2p orbital on carbon. What do I have? I have 1 electron on the unhybridized carbon. I don't only have that on that side, I also have it on here. What can I form? Oh, guess what? They can overlap sideways, right? So that thing overlap sideways. Remember earlier, you have 1 electrons in each of the unhybridized 2p orbitals, so 1 here and 1 here, but the electrons are moving, yeah, because they are p orbitals, so they're always moving around. The electrons are not static, they are dynamic. Okay, so electrons circulate around, but you got 1 electrons in these p orbitals which are unhybridized, and another one in this p orbital which is unhybridized. They overlap sideways and they give you a pi bond. Give you 1 time pi bond. Alright, so that's why we don't count the pi bond as part of the bonding pair. Okay, that's the reason, because we don't count the pi bond as part of what we want when we form the hybrid orbital, which was mixed in order to give you the sigma bond. Alright, so if I were you, I would go away and try and practice the explanation to think about what is going on with the hybrid orbitals, how I get sp2 in terms of 3 sigma bond around each carbon, and leaving you 1 unhybridized p orbital from the carbon with 1 electrons, therefore giving you a pi bond. Same there, that's how you get a pi bond. Same thing there, that's how you get a pi bond. Same thing there, that's how you get a pi bond. Alright. Moving on, we'll talk about the last example, which is actually to do with carbon sp hybridization. Earlier we talked about sp3, sp2, now we talk about sp. So this is about 50% S character. There's quite a lot of S character in here, yeah? So you can imagine it will look even smaller. Again, they all look pretty similar, but it's a mixture. It's a mixture of S and a P. Well, I should probably use the correct orientation of the P. So this is dumbbell. Okay, and this is the S. And you use 1 times that and 1 times that. This is of the carbon 1s. This is of the carbon 2p. This is your 2 times. So it's actually 2 times. You mix 1 orbital with another one. 1 orbital plus 1 orbital give you 2 orbital. What kind of orbital? It gives you a S1P1, which is just sp hybrid orbital. Okay. In terms of energy, so I can go a little bit faster now because you are advanced enough, I hope. What happened is I have that electrons there. Okay, maybe I should use the same color. Nope, that. Okay, so now I know I still need to average them, but I only want 2. I only want 2 of the hybrid orbitals because I only mix 1 of the S and 1 of the P. What does that mean? I mean that I have 2 times 2p. The 2p belongs to the carbon, yeah? So I have 2 of that, which are unhybridized. Because they are unhybridized, these are still atomic orbital, and this one is hybridized. When they are hybridized, I get 2 times sp hybrid orbitals, but again, I still have the 1s electrons, and this is the hybridized, and this is the unhybridized carbon atom. We don't use the inner shell electrons for bonding, yeah? So these are the two electrons in the 2p orbitals that remain unhybridized. I still have 4 electrons, okay? But I only form 2 times sigma. That's why I only need sp hybridized. So what kind of thing has sp hybridization? You might not have seen it a lot before, but you will have come across it when you do your dot and cross. This is a HCN, this is molecule. You will use this in organic chemistry under nucleophilic addition, and I will have a video on nucleophilic addition mechanism, which is actually one of the case study across the different A-level examination body. One of the things you need to know before you go to university to study higher level chemistry. Okay, so what do we see in this HCN? Well, you have a H, you have a C, you have an N. We talked in the other video on shape of molecule. So around the central carbon, I hope you can see that the number of bond pair, because this is a 1 sigma, there are 2 pi. There are 3 covalent bond. There can only be a maximum of 1 sigma because of how the sigma covalent bond is formed. If you get 2 sigma, the electrons in the sigma bond will repel so much. That's why you only form a maximum of 1 sigma in multiple bond. That means the other 2 covalent bond must be pi. We count only the sigma around the central carbon. So 1 sigma here, 1 sigma here, 1 plus 1 is 2. But there is no lone pair because the carbon use 1, 2, 3, 4. Use all 4 of its outer shell electrons for bonding. Carbon has 4 outer shell electrons that it has used all 4 for bonding. We talk about the 2 bond pair repel equally. So the 2 bond pair repel equally. You get a linear 180 degree. Alright, but how are the two, what is the hybridization there? And also how are the pi bond being formed? Well, if I draw this thing, I draw the sigma bond as just line. That means I also have unhybridized orbitals, okay? On the nitrogen, I have 1 electrons on the carbon, like that. I actually have 2 of the 2p orbitals that are unhybridized because I only form 2 sigma bond. I only form 2 sigma bond, 1, 2 on my carbon with no lone pair. 2 bond pair here refer to 2 sigma bond. 2 sigma bond would mean the hybridization is, well, that, which is sp. 1 plus 1, mixing one of the 2s, mixing one of the 2p, 1 plus 1 give you 2, okay, of the sp hybrid orbitals, forming 2 covalent, right, forming 2 sigma bond, giving you 2 bond pair in this structure here. Alright, so it still has 2 electrons in the 2p orbitals which are unhybridized. Okay, I've shown them in the plane here. So where are the 2 orbitals? One of them is shown here. So what I've shown is 1 electron in this p orbital which is unhybridized will share electrons, 1 electron on the nitrogen here, on another p orbital which is of the same shape. So they overlap sideway. That will give you 1 time pi bond. Okay, this is 1 pi bond. Okay, these are orbitals, the electrons are always moving around. This is not 2 pi bond, this is 1 pi bond. They belong as a set above and below the plane. As you will know it when you cover pi bond formation. The other one is pointing away into the paper as well as coming out towards you, looking at you right in the eye. But I'll try to show it in a way that is actually showing like 3-dimensional. Again, I'm not the best drawer in the world, I'm not the best artist. So this pink and the green one, they are 90 degrees to each other. If you remember how a p orbital will look like, you can think of them as like that. So I'm going to draw the combination of them. Okay, whereas where's the other one? The other one which is along here, nope, that doesn't work. I've drawn the wrong one. Okay, that works. Alright, cool. So you should label the axis X, Y, Z randomly, I guess. The one which is along the axis, the p orbital has been used to form the covalent bond because it has been involved in hybridization. The 2 p orbitals that are unhybridized, one is on top and below, the other one is in and out. 1 covalent bond, and then the other one is another covalent bond. 1 time pi bond. So altogether, you get 1 plus 1, which give you 2 pi bond. you get one sigma bond along here, but you get another sigma bond. So 2 sigma bond on the carbon, 2 bond pair, sp hybridized carbon. Okay, so that is a carbon sp hybridized. And whenever you get a carbon sp hybridized, it's a 180-degree linear geometry. Okay, where else do you see a linear carbon? Where else? Okay, there is another molecule which you don't do in A level, but you can imagine this thing is called an alkyne. Okay, and this carbon has 1 sigma bond on the here, 1 sigma and 2 pi and 1 sigma. So altogether this carbon has 2 sigma, and it will have this sp hybrid 180-degree linear geometry as well. Okay, yeah, I mean that's it really on hybridization. So I hope that video helps. This video helps in breaking down the concept of hybridization to you and how to work out hybridization very quickly. What I can tell you also is, I should probably remind you of this, you can also work out hybridization on other atoms which are not carbon. So I better finish this off like that. So when you have ammonia, okay, the nitrogen has a hybridization. Okay, the nitrogen has a hybridization. The number of bond pair on the nitrogen is 3 because only 3 sigma, right? The number of lone pair is 1. Okay, the thing about what we have covered so far is none of the carbon has any lone pair. None of the carbon has any lone pair. So it's nice and easy, right? None of the carbon has any lone pair. Okay, in actuality, if they have a lone pair, the lone pairs, you have to count them such that you add them up. This is called electron pair. So the number of electron pair is the number of bonding pair plus number of lone pair, give you 4. To get 4, you need to use the 2s and the 2p of the nitrogen for bonding. You will get s, only one of them. How do you get to 4? It must be 1 plus 3. Therefore, it is a nitrogen sp3 hybrid. Okay, that's how you work out the hybridization very quickly. Okay, the main difference with the organic compound is that you didn't have lone pair, so you don't have to worry about that. But okay, let me do more thing with a lone pair. Let's think about water. So you can go away and practice this on other example. So number of bond pair there is 2. The number of lone pair there is 2. So we know it is a bent 104-degree. We know this is a 107-degree trigonal pyramidal, and we covered this in the VSEPR video, part 2, where I talk about the effect of lone pair repulsion opposed to lone pair bond pair repulsion, as opposed to bond pair repulsion. Yeah. So here you get 4 electron pair again, and you use the electron pair to work out the hybridization. To get to 4, you need 3 of the P. So it's an oxygen sp3 hybrid again. Alright, so really this time I will leave the video here, and if you're interested, you can always find out more from your teacher and read out more online on hybridization. But this is a quick video on trying to break down the concept of hybridization, and in reality most exam questions will just ask you what is the hybridization, state the hybridization. Okay, apart from the organic chemistry where they actually ask you to describe, compare and contrast, the chemistry, the structure, the bonding between alkene versus benzene, for example. Then you can talk about the sp2 hybridization, 120-degree trigonal planar. Then you can talk about alkene, when you have cyclohexane. Cyclohexane is like this, but there's no double bond, whereas you have 2 hydrogen on each carbon. Okay, yeah, so if you like my explanation, please subscribe to the channel, and let me know what else to cover in the future. I'll try to address it in future videos, and thank you for watching.